All right, we're in section 2.2. We're going to talk about polynomial functions with a higher degree than 2. So we talked last time about polynomial functions, what a polynomial was, how we wrote it, and then we spent a little bit of time talking about quadratic functions. We want to talk about some properties of polynomials, what happens when we have degrees higher than 2, what the graph looks like, how the function behaves, and just try to gather some information about our functions. So that's what we're looking at today. So a couple of things important things to note about polynomials. If we're looking at the graphs of polynomials, polynomials are continuous. Now what that means is polynomials they're smooth. There aren't any breaks or gaps in graphs of polynomials. So anytime when we talk about a function with an asymptote, function with a hole, those would not be represented by polynomials. So anytime we have some kind of function where we have a gap in the function, this would not be a polynomial. Because it has a gap or a break. Same thing with an asymptote. If we have a vertical asymptote, we're not going to be talking about a polynomial. Graphs of polynomials are smooth. So they don't have any sharp turns. This is the way we think of it intuitively. So the absolute value function, where we have something like this, would not be a polynomial because we have a sharp turn right here at the origin. And both of these properties will be very important when you go on to study calculus. So what I want to start very quickly with today is to look at some graphs of what we call power functions. So power functions are kind of our most simple polynomial with an exponent. We're looking at f of x equals x to the n. And I just want to look at the graphs of some of these power functions. So here we go to this, and I'm going to grab a picture of this so it shows up on the page of notes. So and let me undo that. I want that on a new page. So do this. Do this. Go. So here are some graphs of power functions. So the black one x squared, red one x to the 4th, blue one x to the 6th, and green one x to the 8th. So our even numbers. So notice with our even numbers, they behave kind of like parabolas. They open up. Because our number here is positive, they all go through the origin, and notice that the parabola is kind of the most curvy, and the others flatten out here along the x-axis, and then go up. So the graphs kind of flatten out. So I just wanted to show you what these power functions are. Let's take a look at power functions where our exponent is odd. So let me grab these. And we'll put these just below on the same page. Make this a little smaller. So here are power functions when our exponent is odd. So they all look more or less like f of x equals x cubed, which is the black one here. And then we graph x to the 5th in red, x to the 7th in blue, and x to the 9th in green. And notice how these kind of flatten out along the x-axis close to the origin also. So some similarities here. Notice how the even functions go up on both sides, the odd functions go up on one side and down on the other side. That's going to be an important property of power functions. And then I have some graphs of some other functions, just some polynomial functions, just so we can take a look at those. So let me grab those. Move this up a little bit. We'll grab a picture of that. So here are some graphs of polynomial functions with even exponents. So we have in black we have a quadratic function, red we have a quadratic function, the one in black is shifted, the one in blue we have a 4th to the 4th power. Notice how they still open up on both sides, go up on both sides. And in green here we have a 4th power, but a negative sign in front. So that turns it over. And notice how they're smooth, nice smooth turns. And then I have some cubics graph, so let's grab those on the next page here. So here's some odd power functions, and we'll grab those and just put those with the other ones. So there are some power functions with odd exponents. And again, notice how they go down on one side, up on the other. The one in blue has a negative sign, so it's turned over compared to the others. So I just wanted to give a general idea of what our power functions are going to look like, what our polynomial functions are going to look like, and this gives us an idea of how we're going to analyze their behavior. So a couple of important things to notice here is that on the even functions, they either go up on both sides or they go down on both sides. The odd functions, the highest power odd, goes up on one side and down on the other side. If it's turned over, it does the opposite. That's going to be true in general of a polynomial function. So this leads us to our first way of analyzing a polynomial function. And that is the leading coefficient test. With the leading coefficient test, we are interested in what happens to our function as x gets very large, as x gets larger and larger in the positive direction and larger in magnitude in the negative direction. Does the function does it keep increasing? Does it keep decreasing? Polynomials will always either keep increasing or keep decreasing as x gets very large or x gets very large negative. The leading coefficient tells us how that's going to happen. So we already know that we talked about when we talked about quadratic functions, that if the leading coefficient is positive, our parabola opens up. If the leading coefficient is negative, our parabola opens down. Well, that turns out to be true for any polynomial when the exponent is even. So for a polynomial with the highest power even, so we're talking about polynomials here. If the leading coefficient is positive, so the leading coefficient, so if I write my polynomial f of x equals a sub n x to the n plus dot dot dot, this is my highest power and this is my leading coefficient. This a sub n is my leading coefficient. So if the highest power is even, n is even, and the leading coefficient is positive, then my polynomial function is going to go up on both ends. Eventually. And what we usually do is draw a little picture. So this shows what happens with our polynomial eventually. It could do a lot of other things in between, but eventually as x gets very large, it's going to keep increasing on both sides. The leading coefficient is negative. Then it goes down on both ends. And we usually just draw a little picture like so. So if our highest power is even and our leading coefficient is positive, we say the end behavior, if we apply the leading coefficient test, the function goes up on both ends, leading coefficient positive, down on both ends, leading coefficient negative. So this is our leading coefficient test. It tells us what happens to our function eventually. All polynomials either get very large or very small, or very large negative. We just want to know how it happens. If our leading coefficient, or I'm sorry, if our highest exponent, highest power is negative, sorry, not negative, odd. Highest power is odd. And our leading coefficient is positive. Then our function goes down on the left and up on the right. And we usually draw a picture, just a little diagram, like that. So eventually, if our highest power is odd and the leading coefficient is positive, this is what our function is going to look like as x gets very large negative and as x gets very large positive. You can do a lot of things in between, but eventually this is what's going to happen to our function. And then it just flips if our leading coefficient is negative. It goes up on the left and down on the right. So eventually our graph of our polynomial function looks like this. And it's important when we're looking at problems that have to do with the leading coefficient, make sure a lot of times they'll try to put the terms of the polynomial out of order to try to trick you, to try to pick the wrong term that has the highest power. So I was looking for the leading coefficient test to talk about the end behavior. We want to pick out the term with the highest exponent on our variable. All right. Another thing we mentioned when we were talking about quadratic functions was zeros. And we said zeros were related to several different important things that had to do with the function. We talked about finding the zeros. We talked about finding the x-intercepts. We talked about finding the solutions. And I also mentioned factors of polynomials. All of those things are related. So here we're talking about a polynomial f. And the numbers we're talking about, again, are real numbers. So all of these things that we're going to list are all equivalent statements. They all mean the same thing. We can use them interchangeably. We can use them to ask questions about polynomials in different ways when really we're asking the same thing. And the reason we ask them in a different way is because it gives us different ways of getting the information that we need. So if we say that x equals a, some number is a 0, that means the same thing as saying that x equals a is a solution of the equation f of x equals 0. We're saying this is a 0 of the function. It's the same as saying it's a solution of this equation f of x equals 0. That is also the same thing as saying that x minus a is a factor of this function. So we can factor this term out. We can use that to factor our function. And this also means the same thing as the point a0 is an x-intercept. And notice when we're talking about an intercept, we're talking about a point. So all of these mean the same thing. If x equals a is a 0, that means that the point a0 is an x-intercept of the graph of that. X equals a is a solution of f of x equals 0 means x minus a is a factor. All of these things mean the same thing. We can tell something about the number of zeros based on the degree of the polynomial. By the degree, we're talking about the highest exponent on our variable. And that helps us work on these things. So if our polynomial function has degree n, so the highest exponent on our variable is n. Then it has at most n real zeros and at most n minus 1 relative maximum points or minimum points. So think about our quadratic function. Quadratic function, the highest degree is 2. That tells us that a quadratic function has at most 2 real zeros. It can cross the x-axis at most 2 times. To cross it again, it would have to curve around again. And we know that quadratic functions, graphs of quadratic functions don't. And it has at most, a quadratic function has at most 1 relative maximum or minimum at the vertex. A polynomial with degree 3 would have at most 3 real zeros, and it would have at most 2 relative maximum or minimum points. So this gives us an important tool to work with our polynomial functions. All right. Finding zeros of polynomial functions is one of the most important things, most important tools that we'll develop in all of algebra. That's an extremely important thing. So that's really a big part of what we're going to focus on in chapter 2 is finding zeros. So let's do an example that involves finding zeros. So I just want to do one example of finding the zero because this has a nice factoring method. So we want to find the x-intercepts of f of x equals x cubed minus x squared minus x plus 1. Well, solving a cubic equation, there is a formula for solving cubic equations. It's not particularly nice. It's not particularly easy to use. It's not extremely clear here what a solution is going to be, but it turns out we can factor this. This is a nice factor by grouping. So we want to find the x-intercepts. That is the same as saying we want to find where x cubed minus x squared minus x plus 1 equals 0. We said those are equivalent statements. Finding the x-intercept is we're finding the x value where this equation equals 0. I'm going to factor an x out here. I'm going to factor an x squared out. I can take x squared is common to these two terms. And I'm going to factor this as well. So these are my groups. I'm going to factor an x squared out. I end up with x minus 1. And I'm going to factor a negative 1 out of this parentheses. Minus 1 times x minus 1. And I'm going to check by distributing again. I get a minus x and a plus 1 here. And this equals 0. Well, now I have a common term of x minus 1 with both of these, so I can factor that out. So this gives me x minus 1 times x squared minus 1. And that equals 0. So we did a nice factor by grouping. And we can check our work by distributing here. I get an x minus 1 times x squared and an x minus 1 times x times negative 1. So we've done our factoring right. And I can factor one more time, x minus 1. This is x plus 1, x minus 1 equals 0. So I have these two, x minus 1, so I'm going to rewrite that as x minus 1 squared times x plus 1, and that equals 0. Well, now I know what the x-intercepts or the zeros are here, or the factors. I've found the factors. So x equals 1, and x equals negative 1 are the x coordinates of my intercepts. So the intercepts are at 1, 0, and negative 1, 0. Now there's one important thing that came out of this example. This x minus 1 is squared. We call that a repeated 0. So this x equals 1 is a repeated 0. And we say its multiplicity is 2. So it's repeated and its multiplicity is 2 because I have two factors of x minus 1. So x equals 1 shows up twice here. So x equals 1 is going to show up twice in our list of solutions. So we call that a repeated 0, and the number of times it repeats is its multiplicity. That tells us something nice about the graph. So we have a nice rule that goes along with that. So if a factor, and I'm going to say x minus a is just some number, and instead of if, I'm going to say for a factor. For a factor, x minus a to the k, where k is some positive number, k is greater than 1. We say that a is a repeated 0. Of multiplicity k. And this is the good piece of information that tells us about the graph. If k is odd, so if the multiplicity of the root is odd, the graph crosses the x-axis at x equals a. If k is even, the graph touches the x-axis. At x equals a. But it does not cross it. So we can tell if our graph crosses the x-axis or touches the x-axis at a 0 based on the multiplicity of the root. So if we think of a line, well, any solution to a line is going to have multiplicity 1. So a line can only cross the x-axis. If we think of a parabola can cross the x-axis twice. So the multiplicity of each of those roots would be 1. Or we could have something like x minus 1 squared, or y equals x squared. The multiplicity of the root there is 2. So the graph just touches the axis at that point. So this gives us a nice way to decide if our graph crosses the axis or touches the axis. All right, one last thing to talk about. The intermediate value theorem. The intermediate value theorem is if we draw a picture, it makes total sense. So for the intermediate value theorem, we have some function, some polynomial. So there's my polynomial. And I'm going to call this point A. And this point B. And I don't know what kind of polynomial this is. And this point is f of A. And this point is f of B. What the intermediate value theorem tells us is when we have a polynomial function, when we have a continuous function, the function is going to take on every value between f of A and f of B. So there aren't any holes in our graph. So if f of A is 7 and f of B is 11, then for some point inside this region, we're going to be able to find a function value for every number between 7 and 11. So some x is going to give us some function value 7 and 11 because our polynomial is smooth. There aren't any holes in it. There aren't any gaps. So it takes on every value in between those two. And the way that we usually use the intermediate value theorem is that if we know that our function is increasing, so for example, if we have a function and we know over here our function is negative and over here our function is positive, that somewhere between those 2 points the function has to equal 0. So here it's negative, here it's positive. Somewhere between those two it has to equal 0. That's usually how we use the intermediate value. Now so if we know it's negative here, we know it's positive there, then at some point in between those two, it has to go through 0. All right, really quickly before we finish, some of the problems that we'll work on ask us to sketch graphs of polynomial functions by hand. The process that we're going to use to sketch by hand, we're going to use the leading coefficient test to decide what the end behavior is. So the right and left hand behavior, what happens on the right and left hand side. We're going to find the zeros, we're going to find the x-intercepts, plot those, and then we're going to plot additional points just by plugging convenient numbers into our function and calculating some additional points that go on our graph. So we know what happens eventually on the right and left hand side. We can find the zeros, so we can find the x-intercepts, plot those points on our x-axis, and then we plug in some points into our function to get some points in between, and then we connect them with a nice smooth curve. And the intermediate value theorem, we can use the intermediate value theorem to help us decide where a zero might be. We know it's negative here and positive here, then the intermediate value theorem tells us it has to go through 0. All right. And our homework, we'll work on this in class, but our homework for this section, if you want to try some of the problems, you can find it here. Second. Page 109. And this first set of problems goes very quickly. All right, and there it is.